All right, good morning, everybody. Today is Code Forces round 663. I'll be competing live and sharing my thought process throughout the contest, and then after contest, I'll go over the solutions to all the problems I know how to solve, as usual. Good luck to everyone who's competing, and I'll see you on the scoreboard. Let's begin. All right, problem A, sub-arrays. Permutation of length n is an array of n distinct integers. We know what a permutation is. For a positive integer n, we call a permutation good if the following condition holds for every pair I and j. The OR of the range is bigger than the length of the range. Or is at least as big as the length of the range. For a given integer n, print any good permutation. Just increasing works, right? Just the identity permutation should be fine, I think. Yeah. Oops, that was problem template, not problem A, but let's try it anyway. Yeah, I think that's fine.
Well done, sir. Facing your problem now.
All right, on to problem B. Consider a conveyor belt represented using a grid consisting of n rows and m columns. The cell in the ith row on the top and jth row from the left is labeled ij. For every cell except the bottom right has a direction right or down. If it's assigned right, any luggage will move to the right cell. It's row column. Okay, every cell moves right, otherwise it moves down. Yeah. There is a cell, there's a counter in that cell where the luggage will be picked. The conveyor belt is called functional if and only if any luggage reaches the counter regardless of where it's initially placed. This may not hold initially, however, you are allowed to change the directions of some cells to keep the conveyor belt functional. Please determine the minimum amount of cells you have to change. It is always possible to make the conveyor belt functional by changing the direction of some sets of cells. Well, if they all move right or down, you just need all the things on the bottom to be right and all the things on the right side to be down, and the rest doesn't matter. So these all need to be right. So this is 3, this is 1, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, sounds good. Where did x height minus 1 is not equal to the right, then c++. And for int y equals 0, y plus 1 is less than height, y plus plus. If board at width minus 1, y is not equal to down, counter plus plus. Mm-hmm. Next one out of bounds for length 1 shouldn't be length 1. Oh, width by height. All right, on to problem C. Cyclic permutations. A permutation of length n consisting of n distinct integers. They already defined a permutation earlier in this problem. Consider earlier in the set. Problem A. Consider a permutation of length n. We build a graph of size n as follows. For every I less than n, find the largest I. All right, hang on. I have to read this actually. Find the largest j that comes before it. Okay, find the last thing that was bigger than it, basically. So the last thing bigger than you, there's an edge from you to it. And then the first thing smaller than you, Pj is greater than Pi. Oh, the first thing bigger than you to the right. First thing bigger than you to the left, first thing bigger than you to the right. I see. Permutation is called cyclic if the graph built has at least one simple cycle. Given n, find the number of cyclic permutations of length n. Huh, that's an interesting question. I think a more interesting question might be, how many non-cyclic permutations of length n are there? Because I think most permutations would be cyclic. So what is 4 factorial? 24? That means there are quite a few non-cyclic permutations. Let's think about what it means to not be cyclic. If you have 1, 2, 3, 4, then you'll have these edges. Well, okay, so let's look at the 3 case, I guess. If you have 1, 2, 3, then you have these, so that's okay. If you have 1, 3, 2, you've got this and this, which is also okay. But if you have 2, 1, 3, then you have an issue, because you have this and also this. So if you ever have something that looks like this, then you have a problem. If you ever have some integer, like if we go smallest to biggest, we've got this integer here. If we have a thing bigger than it on both the left and the right, then there's either going to be an edge like this or the other way. So we can't ever have that, which means the smallest thing needs to be on either the left side or the right side. So is the answer going to be n factorial minus like 2 to the n or something? 2 to the n minus 1? Because the last item we don't have a choice for. I think so. Let's code that up because it'll be really quick to code up at least. Where we have C. Single test case even. Ten to the ninth plus 7. Yeah, okay. 4 int I equals 1, I is less than or equal to n, I plus plus, ants equals ants times I mod. Long to pow equals 1, 4 int I equals 1, I is less than n, I plus plus, 2 pow equals 2 pow times 2 mod sys out ants minus 2 pow plus the mod. Yeah, you always get suspicious when they don't give you any test cases to actually show you the problem. It's never a good sign. I think that's fine. This is a more reasonable like difficulty div 2, I think. The last one was just ridiculously difficult. Binary matrix is called good if every even length square submatrix has an odd number of ones. Even length meaning the length of the side of the square is even, probably, I assume. Given a binary matrix A consisting of this many things, determine the minimum number of cells you need to change to make it good, or report that there are no ways to make it good at all. I see. It's an interesting question. I like it. I suspect it's already been solved though, because I have an idea right away. It hasn't. Interesting. Two people have gotten it wrong too. Well, here's my idea. If you've got some square or some matrix here, then if you look at the top group of 4, like there aren't that many ways of doing the top group of 4. You need one, like if this is on, then that forces this to be on, this to be on. Like it forces a bunch of things. Oh, that's not true. So if that's the only one on, if you move right, yeah, if it looks like that, all right, what does that tell us? So if we move right, we need one of these two to be on. If we move down, we need one of these two to be on. if we move right again, we need 0 or both of these to be on. Wait, what did they say? This is very suspicious. If every even submatrix has an odd number of ones. So, yeah, okay. Another idea, which is this. If you have a 4x4, it's impossible. Here's why. If this is even, or if this is odd, this is odd, this is odd, and this is odd, then this thing right here will have the number of ones, and it will be the sum of 4 odd numbers, which will be even. So if it's 4x4, that's impossible. So we can just do a 2 to the n and then check. Is it multi-test case or no? It's not. Oh, is that true? Yeah, it is true. In fact, if it has a 2x4 in it even. Now, what is an even length square submatrix? Okay, so, well, there's the 1 by n case, which is all ones. Then if it's 2 by whatever, if this question mark is greater than or equal to 4, then it's impossible. Otherwise, we can do whatever, because it's quite small. The biggest you can get is 3 by 3. Yeah. So it's just very brute forcey. Cool problem, though. I really like the problem. I figured it out quick, so I might be biased yet again, but I think it's a cool problem. Single test case. N equals the height. Let's do height. This equals this. Math dot min of width height is equal to 1. Then this is the 1 by n case, which we need to handle. Return. If math dot max of width height is greater than 3, then sys out -1. Return. Okay, otherwise brute force. So let's handle this. Okay, so int answer equals 0. Set the answer. For int y equals 0, y is less than height, y plus plus. Carry line goes this. For char c in line, c is equal to 0, then int plus plus. Okay, that handles that. Now for this one, it's impossible, otherwise we brute force it. Okay, public static boolean works. Boolean board. So we only need to check 2 by 2s, right? So the dimensions can be, you can't have anything any dimension of 4, so check 2 by 2s. So for int x1 equals 0, x1 plus 1 is less than board dot length, x1 plus plus. For int y1 equals 0, y1 plus 1 is less than board at x1 dot length, y1 plus plus, int count. Return true if we don't find any break cases. Int x equals 0, x less than x 0, 2, x plus plus. Y equals 0, y is less than 2, y plus plus. If board at x plus x1 and y plus y1. And count plus plus. If count mod2 is 0, return false. For int mask is equal to 0, mask is less than 1 left shift width plus height, mask plus plus. Yeah, okay. Boolean array clone equals new Boolean array width by height. All right. Very good. Yeah, okay. Board it with height equals 1. Okay, so now for int x equals 0, let's look at the position too and the mask. Okay, so if mask and 1 left shift the position is not if this is not equal to 0, then clone xy XOR equals true. Okay, int equals width times height, all equals integer dot max value. If ants is equal to integer I'm pretty sure it will always be possible, but just in case it's not, I want to handle that because there might be other impossible qualifications that I haven't thought of yet. So just in case. Now, what do we do for this? Yeah, okay. So if possible, what would I call it? If works, the clone works. Or wait, we have to, yeah, okay. So now if the clone works, then ants equals math.min ants integer.bit count mask. -1, and that's it.
Problem debug wrong answer test reason.
Interesting. Williams winning. Nice job. Why is this wrong though? Oh, it's got to be square. Yeah, it's got to be square. I see. okay, all right, I see. So there are like a couple more cases we need to handle. 2 by n's and 3 by n's, for instance. Yeah, you can't do this. This 2 by 4 thing doesn't work. All right. So let's modify this. If the min is equal to 1, okay. Now, if the minimum of them is greater than 3, then it's -1 in return. Otherwise, we can maybe brute force them. We can do binary or we can do matrix expo at least. Yeah, maybe they're looking for matrix expo. Sounds like that's probably it. So what's the state? 2 to the 6? $64. It's not even 2 to the 6, it's 2 to the 3. Yeah. And also, this 1 by 1 case also isn't right. This is just 0. If it's 1 by n, there are no even rectangles, so this is 0. Alright, if it's greater than 3, the minimum is greater than 3, the answer is 1. So I wasn't really close at all, but this works code might be helpful. Yeah, okay. So we can do a DP, a 2 to the 3 by n DP. Okay, so let's make a Boolean transition matrix, or like, yeah, possible trans matrix, this new Boolean, so it'll be width by width, because, or it'll be 2 to the width by 2 to the width. Yeah, okay. For int m1 equals 0, m1 is less than 1, left shift w, m1 plus plus. So then this will be the matrix. That'll be, oh, I see. Yeah, okay. If width is greater than 3, then we need to flip everything. Okay, so now we can safely work through it width by width. So now this matrix will be width by 2, or int x equals 0 x width x plus plus. The first level of the matrix, the m1 and 1 to the width is not equal to 0. Second level of the matrix will be the same thing but with m2. So now we've got our transition matrix. So one left shift width by height. So for int x equals 0, x less than 1 left shift width x plus plus. Let's make int array masks as new int. How big is this going to be? Height y equals 0. Y is less than height. Int mask equals 0 for int x equals 0, x less than width x plus plus. Mask plus equals. This is only if the board at x, y is equal to a 1. Plus equals 1 left shift x. Masks at y is mask. So we have the mask for every y level. Yeah, we can make this space saving too if we need to. But that's a thing for later, I guess. So now for int y equals, well, we need to fill in all the x's, right? For int x equals 0, x less than 2 to the width, x plus plus. Cost at, let's just make the space saving now. Arrays.fill the cost with int 1e9 maybe. Cost at masks at 0 equals 0. Oh wait. Yeah, no, that's not right. Cost of getting a given mask is equal to the number of bits you'd have to change to get there. Yeah, okay. So now, very good. So now for int I equal, or int y equals 1, y is less than height, y plus plus. Int array new cost equals new int 1 to the width. Then at the end, cost equals new costs. So at the end, int best will be cost 0, or int I in cost. Best equals math.min of best into I. Pass this out. Best is less than 1e9. If it is, print best. Otherwise, print -1. If it's somehow impossible. Okay, so now for int, we're doing this already? Yeah, okay. For new mask equals 0, new mask less than 2 to the width, new mask plus plus, and from equals 0, from is less than 2 to the width, from plus plus, transition, what did I call it? Possible transition, from to new mask. Well, I guess if it's not possible, then continue. If it is possible, new costs at new mask equals math.min, new costs at new mask. Alternatively, we could do cost at from plus integer.bitCount. The bit count of from, or of new masks XORed with the masks at this Y. Okay, raise.fill, new costs with 1e9. Should be 1 left shift X. It should also be 1 left shift X, I think. It should be M2 plus plus. That's some answer. This integer.bitCount scares me though, so let's pre-comp it. How big can this number get? Not very big. Int array bits in equals new int array 100 for, well, let's just say 1 left shift 5. Let's do 1 left shift 7 just to be safe. I equals 0, I is less than 1 shift 7, I plus plus. It's in at I equals integer.bitCount of I. Alright, seems plausible. If my solution's right, you can also solve this problem up to like 10 to the 18 by 10 to the 18. Looks pretty right. So yeah, if you wanted, you could do matrix expo for it.
Well done, sir. Proceed on problem B.
Oh, I didn't need to though. All right, let's solve set. That's the goal. Pairs of pairs. You have a simple, connected, undirected graph consisting of n nodes and m edges. Consider any way to pair some subset of n nodes such that no node is present in more than one pair. I see. When we pair them, do we have to pair them across an edge? The pairing is valid if for every pair of pairs, the induced subgraph containing all 4 nodes, 2 from each pair, has at most 2 edges out of the possible 6 edges. Yeah, okay, so you could have like a square with a box, but only 2 of those can be present. More formally, if for any 2 pairs, the induced subgraph of nodes should have at most 2 edges. Please note the subgraph of an induced set contains only nodes from the set. Yeah, and edges which have both the things there. Okay. Do the following. Do one of the following. Ah, this is the classic. I like these problems. They're fun because they're very difficult. Find a simple graph consisting of ceiling n over 2 nodes. Or find a simple path consisting of ceiling of n over 2 nodes. The path is simple if it does not visit any node multiple times. Or find a valid pairing in which at least this many nodes are paired. It can be shown that it's possible to find at least one of every 2 of the 2 in every graph. Yeah, so there have been a couple problems like this, of this kind of idea, where it's like, you can choose which problem you want to solve. Just please solve at least one of them. Nice win, William. Good job, man. Speedy quick. Yeah, okay. Doesn't have to have an edge between the pairs we pick. I see. So, yeah, I think the interesting thing, it has to have exactly 2. Has at most 2 edges out of the following 6. Oh, it's guaranteed to be connected. How nice of them. Well, if there are a bunch of edges, there's some simple path. Finding a simple path shouldn't be that bad. Like if you have a giant click, then you just do a DFS, you'll find a path. Alright, so we've got some nodes like this. If we have something like this, let's say we choose this pair here, and this pair here. Well, what if we 2-color it? might have like red, red and blue, blue. So that might not be helpful because you could have like that for one. Oh, but hang on, if we two color it, or if we three color it, and we have like a good number of one color, if we have lots of one color, like bigger color, we just take the bigger one. So if it's two colorable, then it's always possible, because one of the colors has at least half of them and there are no edges between two nodes of the same color. But not many graphs are two colorable. It only takes one small cycle of 3 to ruin that. Let's say maybe we consider some DFS tree. Maybe we go down like this, down like this. So if we pick two nodes like this, you want to pick, if you pick two nodes that don't have an edge between them, and two other nodes that don't have an edge between them. You need like only one of these to have a, you can only have, oh wait, yeah, you can have like this, okay. So two coloring is again quite helpful, maybe. If we have red and blue nodes, like if we have this as a red, this is a blue, this is a red, this is a blue. Feels like this will give us a lot of answers. This will be very close to an answer at least. It's hard to break. If we don't have an edge here, and we also don't have an edge here, then there are only two edges that could exist. At the moment though, any construction I would make for this would have no relation to some length of a path. So I wouldn't be at all sure that my solution is right, other than the fact that like, it sounds hard to break. How would I actually go about doing this if I wanted to? Well, two coloring a graph that isn't two colorable is tricky. I guess you could randomize, you could do it maybe like a little bit randomized. Oh, that might not be helpful though. I bet it would fail for the star graph, right? Yeah, it doesn't work for a star graph. If you have a star, then you only have one red node, so you only get one red pair. Yeah, so this idea doesn't work. What if we look at different subtrees in the DFS tree, though? Yeah, maybe this two coloring thing is just like not the right path. Seems like there are lots of problems. If we look at, if you've got two different subtrees in your DFS tree, because that has a very direct relation to length, then if you have this thing here, this thing here, if you pair these up like this, you won't have edges. Yeah, you'll never have this edge here or this edge here. And then you also want to have this edge here or this edge here. So that seems like a solution. So what's the idea? We return the number of unpaired nodes in our DFS subtree after doing this DFS. So we can return this here and this here. If we return these two sets, then yeah, okay. Seems like this works. How do we get a proof? So if there's some path that's length n over 2, then it's impossible. If there's no path that's length n over 2, we always pair something with that path, right? Then everything else could get paired with that path. Can we do just like the Euler tour thing? So what if we do, yeah, because back edges are never helpful. Yeah, so back edges aren't relevant because we won't pair you with your ancestor, we'll only pair you with your neighbor. Oh, this might be super cool. Oh, we just get the biggest path. Here's another idea. We just get the biggest path. Everything that's in this longest path, in this DFS tree, if it's in this path, yeah. Okay, so if this is n over 2, this is greater than n over 2, we take the path. If it's less than n over 2, that means we can take any other thing and match it with this thing in the path. That's really easy. Or not necessarily something in the path, but something else. Yeah. So how does this work? If we need to match everything that's not in this path. So for each node in the DFS tree, or for each node that we're DFSing from, we need to sort Does it even matter if we sort them? We can just like match pairs greedily, I think. From different subtrees? Yeah, I think that's fine. Okay. How much time? Plenty of time. Public, all static class node, ArrayList node adjacent. Public void DFS 0. So we want. What if we can just do this all in one DFS? That might be nice. Boolean visited. Alright, so for node O in our adjacencies, if O is equal to from, then continue, because that's our parent. If O dot visited, then continue, because that's a back edge. Okay, otherwise O dot DFS from this node. Int ID, node int ID, this dot ID is ID. Maybe this returns an array list node of nodes. What? Okay, thank you. And then we should also store our parent and our depth. Depth. All right. Yeah, so we've got this DFS going on. So it returns the unmatched things. Static array list node group 1, or like first of pair, second of pair. So for each pair we'll put them in these array lists. A single test case, it's multi-test case. Why do we keep alternating between single and multi-test case? I don't really get it. Alright, so now first of pair dot clear, second of pair dot clear. Alright, so now when we do this DFS, blah blah blah, array list node unpaired equals this. Okay, so array list node. Well, let's keep this array list. This will be like what we have left. Yeah, okay, so that should be fine. So now for array list bigger. Oh, this is kind of annoying. Yeah, this is very annoying. This should be an array deck. Let's just do that. And let's have this just return an array deck. And now that makes everything so much easier. Okay. Very good. Okay, so now I don't need to worry about all of this nonsense. So now, while not have left is empty, and also unpaired is empty, then we can remove from both of them. Then while not unpaired is empty, then have left dot add unpaired dot remove. Okay, so that will do a bunch of stuff for us. We'll get a bunch of pairs from that. Now we need to build our graph. I think I forgot to set visited too even. Okay. So now nodes at 0.dfs from nothing, depth 0. Well, depth 1, because we're counting the number of nodes in the chain, right? Yeah. So now for node n in nodes, if, what do we print? Okay, so output pairing or path, number of pairs or length of the path. Yeah. Okay, so for each of these nodes, if nn.depth times 2 is greater than or equal to n, then sys out this node. Well, okay, then sys out path. Then sys out. How do we do this? We print the number of nodes in the path. This is pairing, path, print. Yeah, okay. The number of nodes in the path. So print nn.depth. Then print the vertices in the order they appear. So while nn.parent is not equal to null, sys out nn.id equals a space, and then sys out at the end this node, which has null as a parent because that's the root. Once we do that, we continue the outer loop. Good. Okay. Now if first of pair dot size plus second of pair dot size. This times 2 is greater than or equal to n. And sys out pairing. Otherwise, throw null, because something is wrong with our proof. Then what do we print? The number of pairs. Sys out first of pair dot size. Yeah, okay. I think this is fine. What just happened there? Hello? Okay, let's just try this like one at a time maybe. So 1, 2, 3, 4, 5. Like an infinite loop or something? They printed path, then the depth. Oh yeah, duh. nn equals nn dot pair. Dot ID. 251. 251. I guess that's technically correct. Because that contains half the nodes. So, sure, it's uninteresting, but it works. So 251, the second case, is that just the same graph? Did they just give us the same thing twice? Okay, fine. Here's an invalid pairing for the same graph. Here's the pairing output for the third case. So I do 10 and 11. Well, do I want to check this? Maybe. 10 and 11, okay. 4 and 8. 4 and 8. Okay. 9 and 6. Wait, 10 and 11 and 4 and 8. Hmm. 9 and 6. Okay. 3 and 7. 2 and 5. Yeah, I think that's fine. I think that's fine. Let's submit. Oh wait, we're gonna have problems. Darn it. Print writer out. All right, and I think we need stack trick too. Let's make sure we still run. Oh man, this is terrible. I don't want to do this because now we don't crash. So crashable stack trick then. This will be just M with null. Okay, I think that's fine. Could we TLE? What's the time limit? 3 seconds.
Problem got time limit exceeded task 8, sir.
Really? Really? Time limit exceeded, huh? How does that happen? Let's triple check to make sure we're just getting Java here. What are bounds? How big are bounds? It's wacky big. Very, very large. Do we need to convert this from a DFS to a BFS? Well, we might be able to fix this array deck shenanigans. We do one DFS. One DFS. Okay, well, and do we know the max size here? Can I predict the max size? Oh, I'm dumb. Yeah, this needs to be small to big. So yeah, one of these is empty. Yeah. This is stupid. This is just like n squared, actually. If not unpaired dot is empty, then have left equals unpaired. Silly mistake. So that was just n squared. That'd account for everything. Still going to be tight on time. Memory limit exceeded.
Got memory limit exceeded test 16, sir.
What is the am I not using linear memory? Memory limit exceeded? Memory limit exceeded. How do I exceed the memory limit? This? Is linear. Surely it's linear. Should be linear, unless I have a bug. Is it this array list thing? Is that really going to be that bad? Shouldn't be. So maybe it's the array deck, maybe it's the array list, maybe I should just write my own. Cut this down. Family quick at least. Memory limit. I haven't gotten memory limit exceeded in ages on Codeforces. Memory limit exceeded. Yeah, I guess I might as well just write my own array list. Static. Hello. Node list. Int start equals 0, end equals -1. Inside.
Pleasure hearing you work, sir.
We have company.
Understood, sir.
Well, say 5 maybe, or let's say maybe 3. It's hard to tell. We'll do 3. Shouldn't be too bad. Public void add. So if we want to add some node, if end +1 equals nodes dot length, then resize. And now nodes at end +1 equals n. So this will just be ++end. Public node remove, return nodes at start ++. Public boolean is empty. Return start is greater than end. We also need get. Public node get. Well, we don't need get, we can just use these. Okay, so we just need to resize now. So node array resized equals new node array nodes.length times 2. I equals start. I is less than resized. I is less than or equal to end. Plus plus. Resized at I minus start equals nodes at I. Start, well, end minus equals start, start minus equals start. is a node list now. What did I call it? Yeah, node list. But it doesn't need generics. This returns a node list. Oh, yeah, we do need size. Public in size. Turn end minus start plus 1. So while not first of pair dot is empty, then we print first of pair dot remove dot id and second of pair dot remove dot id. Okay. Two, 5, 1. That works. Let's just copy this, make sure it runs. Does not run. Good thing we checked. Oh yeah, duh. Nodes equals resized. Good. Yeah, is that all we need to fix? I don't know. I think it should be. Because it's linear memory. I've said that a bunch, but... Oh wait, no it's not. We have all of the edges here. This is a node list. Int I 0 I is less than node list dot or adjacent dot end less than or equal to this I plus plus node O equals adjacent dot nodes at I. Yeah, okay, good. Wrong answer test 1. Okay, hello.
Problem, you got wrong answer test 1, sir.
Why did I get wrong answer test 1? Oh, yeah, okay. Let's just do this. First of pair equals new node list. Same thing with second of pair. 5 pairs, looks good. Do we MLE? Not looking good. Looks like maybe a TLE. Really? Is there like a bug in our code?
Problem got runtime error test 15, sir.
Runtime error? Because of this? Because of this, or because of the stack not being deep enough? How much memory did I use? Let's make a chain. So out.println I plus 1 plus space plus I plus 2. Well, plus 1. Yeah, okay. 1 I equals 0 is less than n I plus plus. Three, 6. Let's try this, I guess. One test case. That's not right though. Oh yeah, it is. Okay, now let's make this scanner read from f.end. Is it like this? I always forget how to do file input. try catch. All right, so this needs to be bigger. So slow. Oh my goodness. It's ridiculously slow. Well, I guess I'll submit this, and then I have to go to the bathroom. It's annoying.
Well done, sir. KC roll call for you.
I heard it got AC, which is nonsense. Because this whole thing is just a bunch of baloney. That's silly. That's silly. Oh well. Yeah, that's kind of ridiculous. But that's fine. Alright, well, I might as well start solutions. You know, I had the solution so early. How much time did I spend doing this? So, okay, this was wrong, but now this solution was right. So I spent almost 20 minutes fixing that. The solution was right. It was like totally right. Wasn't it? This was, I had already fixed, yeah, I had fixed this. So the only differences between this submission and the one that I seed were getting rid of the built-in Java array lists. I stopped using those, and then decreasing this, which shouldn't matter because it shouldn't use space it doesn't use. It doesn't need. So that's kind of nonsense. I thought the problem set was very good. I enjoyed all the problems. I solved all of them, so I might be looking through them with rose-colored glasses. You know, people say that a lot, rose-colored glasses. Have you ever actually looked through something in like red-tinted? If you tint everything red, everything looks pretty terrible, to be honest. Like from rose-colored glasses, the world looks pretty bad. It's much better to have like maybe like slightly yellow or slightly like maybe bluish tinted glasses. I think would be good. Yellow would be decent. Green might be, well, no, maybe not. If everything's green, it might be kind of ugly. But I feel like rose, if you tint everything red, it doesn't make things look good. In my opinion, at least. Whatever. Okay, so let's go for solutions. Problem A. Yeah, okay, so problem A was, I don't know, it was interesting, I guess. I kind of liked it. So you have, like, you have to know what bitwise OR is. But basically, if you have the bitwise OR of some number, like if you have two numbers like this, and maybe this is your other number, if you take their bitwise OR, it's just you write them in binary, and then their OR is if either one of these are 1, then the OR will be 1. So that's what we're looking for. Now, you've got your permutation, and a permutation is just you take the numbers 1 to n and shuffle them in some way. If you like, you might not shuffle them. That's also a permutation. But it's just the numbers 1 through n in some order. So the answer is just print them in their original order. And now the thing to keep in mind is you want the length of any subarray to have an OR that's at least as big as its length. Right? So any subarray has its length and then it has its OR. You want the OR to be at least as big. Well, here's the thing. If we have this permutation here, if we take some subarray then this biggest number here will be part of the subarray. Like the length, we'll have some number that's bigger than the length in the subarray. And all of those 1 bits will be on. So by taking the OR, we'll only make it bigger. So any subarray you pick, if we pick like this subarray here, the subarray is of length 4. The rightmost thing is going to be 4 or bigger. In this case, it's 5. So if we take the OR of all of these numbers, the OR will be bigger than 5. That's like kind of a proof this works. There might be other ways too. If you did them in decreasing order, that would work as well. There's a lot of freedom here. You just have to be, well, I don't know. It's kind of hard to find a strategy that wouldn't work. But anyway, let's talk about problem B, fix U. So yeah, in problem B, you have some conveyor belt. And it's like a 2D conveyor belt, which is kind of neat. To make it even easier, everything will go to the left or to the right or down. An interesting version of this problem might be, what if they don't do that? If they don't necessarily go to the left or to the right and go down, then you might have cycles, which would make things more difficult because then they might like stay on the board forever here. But if they only go right or down, you won't have any cycles. Because like you always, eventually you'll fall off either the right side or the bottom side, or you'll end in this corner. So the corner is like the stationary spot. The thing you have to notice is this space right here, it's got to go down. If it goes right, then if you start on this space, you'll fall off the grid. So this needs to be down. This one, if it goes down, it'll reach the bottom. If it goes to the right, it'll fall off, so it's got to be down. This one also has to be down, so we've got this entire path needs to be down, and for the same reason, this path needs to all be to the right. Now, for everything else, we can look at this as like a smaller subproblem here. But for this problem, if you fall off, then you're still going to land in the right spot. So no matter what all of these things are, it's always going to land in this bottom corner anyway, so we don't even care about all of these positions. So these all have to be down. These all have to be right. If they're not, then you know that's a break case, because if you start at that position, you would fall off. So those are all forced decisions. The rest of these you don't have to change at all. So it's just how many characters do you have to change for these to all line up and also for these to line up. Awesome. Let's talk about problem C. Oh, let me show my code for that. Someone asked earlier to see my code for some of these problems, so that might be helpful. So code for A, it's incredibly simple. It's just print the numbers 1 to n. There you go. Problem B is also quite simple. I read in the board, so this just reads in the board. Then I count how many of these characters need to be changed to right, and then how many of these characters need to be changed to down. All right, now problem C. Cyclic permutations. So here's the thing with this problem. The first thing to notice is, like, let's look at things of size 3, permutations of size 3. If you have a permutation that's 1, 2, 3, this works fine because the edges that you'll construct are like this. Now, I'm going to draw my edges in a directed way from smaller to bigger because I think it makes it easier for me to see. In the real problem, they aren't directed. So if I ever have something that looks like this, that would be a cycle. That's bad. And I want to see, like, is there any group of some number of nodes that has too many edges to be a tree? Okay, anyway. So this is what you would have if you have this permutation. You might also have 1, 3, 2. And in this case, you'd have a permutation, or a tree sort of thing that looks like this. But the interesting permutation to look at is if you have 2, 1, 3, for instance. So in this case, the 1 has an edge to the 2 and an edge to the 3. Just to explain the problem really quickly, each number, you find the first thing bigger than you to the left and the first thing bigger than you to the right. You have an edge to both of those positions. So at most, the graph would have like 2n edges. Really, you just want to see how many edges does it have total. Does it have, I think it'll always be connected, right? So you just want to see, does it have n minus 1 edges? That's the question. And yeah, cool. So basically, if you ever have something like this, you have a problem, because this number here needs to have some edge to something bigger than it. In other words, since we want to have n minus 1 edges, we know everything except for the biggest thing is going to have one edge, at least. It might have two. So we need to make sure it only has one edge, because if one of those has two, then we won't have a total of n minus 1 edges. If we need this 1 to only have one edge, that means you either need the 1 on this side and everything else on this side, or you need the 1 on the other side, and then you need everything bigger than the 1 on the other side. That way the 1 only has one edge going to other things. Yeah, so that's what we're trying to count. Basically, we're trying to count how many of these things. What's the question again? How many have a cyclic permutation? We're going to count how many don't have a cyclic permutation, or how many permutations aren't cyclic. In order to do that, you need each next biggest number to be either on the left side or the right side of the permutation. So the 1 has to be the first or last thing. Now we have this space left for everything else. The 2 has to either be the first thing here or the last thing here. Then we have some space for everything else. So basically, the number of ways we can do this is 2 to the length of the permutation minus 1. Because for everything except for the last position, we can either put it in the beginning or the end. So we have 2 choices for each of those positions. The last thing has to be in its own, in the only space left. So there are this many ways of making a non-cyclic permutation. All of the permutations that aren't non-cyclic have a cycle, and there are n factorial permutations. So the answer is n factorial minus 2 to the n minus 1. Yeah. That's the entire problem. Coming up with that is the hard part. Coding it is not. Coding it looks like this. That's it. So this is get n factorial. This is get 2 to the n. This is print the answer. You don't want to do 1 left shift n minus 1. This will not be the right answer because this doesn't work under mod, because the left shift cycles every 32 steps. So this will give you the answer under like the wrong mod, basically. Yeah. Well, it doesn't really give you the answer under any mod, to be honest. It's just like the wrong answer entirely. That's problem C. Let's talk about problem D, 505. Where did this name come from? No idea. Yeah, okay. Well, so you can solve this problem in 2 ways. I'm going to talk about the easier way, which is what I use to solve it. The first observation is, well, let's talk about the problem first. So you've got some 2D matrix of 1s and 0s, and you want every even square submatrix to have an odd sum. So maybe this is like some 2 by 2 matrix. You want the number of 1s in here to be odd. Then maybe we have some other 2 by 2 matrix. We want the number of 1s in here to be odd as well. So here's the first thing to notice. If we have these 4 2 by 2 matrices, in total this makes a 4 by 4 matrix. And the sum of this 4 by 4 matrix, if the sum here is odd, that means one of these 2 by 2 matrices has to have an even sum. In other words, if all of these have an odd sum, that means the 4 by 4 matrix will have an even sum, because if you add 4 odd numbers, that's the same as adding 2 even numbers, because an odd plus an odd is even. So the sum of 4 odd numbers will be even. So if there's any 4 by 4 matrix, then the answer is going to be impossible. So that cuts out most of the problem. Most of the problem is now very easy. If it's just like a 1 by n, so if it's like that, or if it's like this, I think I special case this, but you don't even need to be honest. Do I special case it? Yeah, I special case it. So if it's just like this, then there are no even matrices, so the answer is just it's okay. You can make 0 changes. But now the other thing is a bit tricky. If it's like a 3 by n, then it can be a pretty big matrix. It can be like 3 by 10 to the 6th, maybe. So you have to be a bit careful with that in what you're doing. And we can do something kind of interesting with it. So say this is the matrix that we want. And some of these things have 1s in them and some have 0s. But we don't know about that quite yet. What we can do is a DP, looking at some given like bottom half of this. And then the state of the DP needs to be, what elements have we not looked at yet? And also, what is this last row? What is the state of this last row? We care about this because we know all of the rectangles that are here or above, all of these are satisfied. All of them are 2 by 2 rectangles since 4 by 4s don't fit. And they all have an odd sum. So in this case, this wouldn't work. So like maybe this was changed and this is like a 0 now. And then maybe something like this was a 1, maybe this is also a 1. So that's all fixed somehow in such a way that these are all known. Now we need to know which ones of these are 1s in order to figure out what things can we place in this row here. We need to keep track of 2 to the 3 because the width is at most 3. It might be 2 to the 2, it might be, well, it won't be 2 to the 1 because we special case that, but you could do that as well. So we need to keep track of at most 3 things here. And we need to keep track of whether each of them are a 1 or a 0. That tells us which states we can hit in the future row. So we're going to look at this DP value here with this thing brute force to some value. And we need to know which pairs of these will match up so we can pre-compute all of those. In other words, for each mask here and each mask here, if you put these 2 masks next to each other, do all of the 2 by 2 rectangles work? So you can just write a brute forcer for that ahead of time and look those up for the 2 masks. And you can see, all right, if we have this mask here, what mask can we place here? For each of those, what's the minimum cost? And then you take the minimum over all of those. I'll open up my code real quick. It's not the cleanest thing in the world, but it's not too bad. If the width is bigger than 3, then you have to swap them so that it's like narrow and tall. Or you could handle it, like you could special case the other one and handle that one separately as well. But I just made it so that it's narrow and tall because the problem is symmetric if you flip it along the x equals y line. Oops. Okay. If it has a 4 by 4 rectangle, we print -1. This is special casing the 1 by n case. Okay, now the other case is first I pre-compute all possible transition matrices. So I say if the top row is this mask and the bottom row is this mask, is that a legal transition? And yeah, so I just have this method just checks all 2 by 2 rectangles and checks if any of them have an even sum, and then returns whether it works or not, because they all need to be an odd sum. So now I have this possible transition matrix, which checks if I can transition from some mask to some other mask. Then initially the cost to reach every possible mask on the top row is just going to be the number of things I'd have to change to reach it. But then for every row below that, this is going to be this new costs array, I check every possible mask that might be above it. For each of those masks, it's either the way of doing the same DP above it with that mask as the bottom one, plus the number of bits I would have to change here. So it's like pretty much the same DP. This bit counts or bits in is because in Java integer.bit count is sometimes slower than you'd like it to be, and I was worried about stupid Java time limit things. Didn't want to get TLE. All right, so that's problem D. Yeah, I think I did a pretty good job explaining that. Let's talk about the last one, problem E. Pairs of pairs. So the idea is you want to do one of 2 things, either find some path in the graph of a certain length, or you want to come up with a bunch of pairs of nodes that includes at least half of the nodes, where if you pick any 2 pairs, the total number of edges between any nodes in those 2 pairs is at most 4. At most 2, sorry. So let's look at that again. You've got this and this. These are your two nodes with a pair. And you have this at, like, this is your first pair. Let me circle it. This is your first pair and this is your second pair. The things you pair up don't necessarily have to have edges between them. Then you can have at most like 2 edges like this, maybe. Something that wouldn't be allowed is if these 3 edges all existed. Alternatively, if these edges existed, that would also be bad. Or if you had like these 3 edges, that'd also be bad. All right, so what's the approach for this problem? Well, the main idea is if you have some graph, you can do a DFS on that graph and get this thing called a DFS tree. The DFS tree, all it is when you take some edge in your DFS, you look at some other node, you see is this visited? If it's not, you go down it and DFS through it. And we can direct all of the edges that we take in that DFS according to the direction we went through them in the DFS. There might be other edges in the DFS we don't go through because we've already visited the edge, the node that edge goes to. So it's possible that we have some edge like this, but we wouldn't take this red edge because it goes to a node we've already visited in our DFS. Now, since this graph is undirected, we only have edges of a certain type. They're either these forward DFS edges, or there are these things called back edges, which always go from some node to one of its ancestors in this tree. In other words, you never have some DFS edge that goes like this, or some red edge that goes like this. If you had this red edge, then your DFS would have taken this edge when it went through the DFS. Instead, it said, okay, this node has no more things it can visit, so it recurses back up the DFS tree, and then it starts DFSing from this node. But if this had more things it could visit, it wouldn't have recursed back up the DFS tree. So that's why you don't have any of these forward edges. You also don't have any back edges, because if you have this back edge, that means you have this edge in the graph, because the graph is undirected. So for a similar reason, you would have taken this forward edge here. Okay, so yeah, so we've got these back edges like this. And here's the idea. If we have any long path in this DFS tree, like formally if we have any path whose total length is n/2 ceiling or greater, then we can just print that path. This isn't necessarily the longest path in the graph, it's just some path that seems pretty long. If our DFS tree only has short paths in it, there might still be some really long path in the graph, but for this, we won't worry about that now. We'll just say, okay, we only have short paths in the DFS tree. Then what we can do is if we're at some node, let me make this a bit more complicated just for a good example. Let's say we're at this node here. We know there are no nodes, there are no edges that connect these two groups. So we can make pairs between these nodes like this maybe. We can pair up these nodes and these nodes here. If we do that, the only edges that there will be like if we have this pair here of these two nodes and this pair of these two nodes, there are only two possible edges because we know these are in different subtrees of the DFS. So no edges cross this line. And also since they're I guess no edges cross that line. That's it. So now those are the only two edges that can possibly exist. So we satisfy the constraint exactly. That means it's totally okay for us to, if we have these two DFS trees, in two different subtrees, we can like pair up things if they're in different subtrees, and that will never have collisions that break the rule that we're trying to follow. If we do that, since the DFS tree is always really shallow, that means the number of nodes that will be unpaired is n/2 floored. Because since it's shallow, we'll only have at most one subtree that goes unpaired, and every other subtree will be paired. The way we can implement this is basically, when we're at some node, we have some set of like things that are unpaired here. We also have some set of unpaired things here. We can like shrink both of them. We can take one from each group, and then we keep doing that until one of them is empty. So finally, when we get to our last group here, we know that at the end we'll just have one group left over, and then we can add ourselves to that group and then return that to our parent. Yeah, okay, that's it. So that's the idea behind that problem. I guess I'll show my code for that too. So I had all sorts of nonsense with MLE issues, TLE issues. It was just stupid because bounds were unnecessarily tight in my opinion. And I'm almost positive this is the intended solution because it's so clean, it's so provable, it's so easy to write an editorial for it. Anyway, so I do this DFS. I'll talk about how the DFS actually works in a minute. And if this node has a depth that's big enough, then I just print the path. If it doesn't have a depth big enough, that means there are going to be enough pairs because of what I proved earlier. So I just print the total number of pairs, and then I print what all of the pairs are. Okay, how do you do this DFS? So the DFS keeps track of several things. Let me move this over in case my webcam is blocking it. There we go. So I keep track of my parent so that I can print the path. I also keep track of my depth, so that I know whether the path will be long enough. I also keep track of whether I'm visited, so I know if an edge I'm considering taking for the DFS tree is actually a back edge and I shouldn't take it. Now, these node lists, this is like the group of unmatched things in previous subtrees that I can make pairs with. That's what this node list represents. This is just like a queue of nodes, basically. The Java built-in data structures caused me to TLE and MLE, so I had to get rid of them for very stupid reasons. But anyway, that's fine. Okay, so now I look through all of my nodes, and I want to look at only DFS forward edges. So this means it's my parent if the edge goes to, I guess, my parent in the DFS. And this means it's a back edge because it's to some node I've already visited in the DFS. Otherwise, I'm going to DFS through this node. So I call DFS on it. I pass me as the parent, and it's one deeper than me in this tree. And this unpaired node means, or this is the list of unpaired things in its subtree. So now I've got the stuff in previous subtrees and the stuff in my subtree. I can combine them repeatedly. That's what this while loop does. And then afterwards, whichever one is non-empty, I make that my current list of unpaired things. And then I keep going through my next kid. At the end, I add myself to it, and then I return this group. And that's it. That's the problem. All right, so I hope you guys enjoyed the contest. I certainly did. I thought it was all very good problems. Let's look at the difficulty, see if it was reasonably difficult or maybe a bit too easy. Maybe a bit too easy. Not bad, though. Not bad. Yeah, I don't know. I think it'll be pretty popular. I think lots of people will enjoy it. Because if you're getting a plus 250 rating boost, you're probably not going to hate on the round, right? And then lots of people are solving lots of problems, which is good. Yeah, maybe this is a bit steep of a difficulty jump. Maybe, so maybe D should have been a bit harder. But, well, this is about a ×5. This is about ×5. No, that's not ×5. What am I saying? That is, well, yeah, it's about 1,000 to 5,000. That's about ×5. So maybe this, maybe like C and D both should have been a bit harder. So this could have been closer to a ×5 gap. But I don't know. I think it's good difficulty. I think this is fine. So anyway, that's the end of the round. Currently, it looks like I'm going to be... Let me see, please. 34th place. Not bad. Good job, Monagon. He sniped me. He didn't have like stupid issues with E though, to be fair, so I don't know, whatever, that's fine. We had almost like identical submit times. It's kind of funny. Oh well. Good job to him. Good job to William for winning. And I hope you all enjoyed the round. That's all for me. Hope you have a great day. And goodbye.